What up, Mr. Sorden here, back at it again with the sick physics instructional videos. Hope you guys are doing good. Alright, we're working on our working energy chapter 7 practice problems. So we're just gonna dive right in. Problem number 1. How much work, also known energy, is needed to lift an object that weighs 200 newtons to a height of 4 meters? So hopefully you guys recall from your note sheets that the work equation is work is equal to the force times the distance. In this case, our force is going to be 200 newtons and our distance is going to be the 4 meters. Okay, so easy calculations, probably don't even need a calculator for that. We're going to get 800. And it's important we can't leave off our units, so if we remember or look back to our notes, we know that work or energy is measured in units of joules. So our answer to number 1 should be 800 joules. Okay. Starting off with a fairly easy one. Whoops. Already drawn all over the screen. Let me see if I can. There we go. Okay, number 2. How much power is needed to lift the 200 newton object to a height of 4 meters in 4 seconds? So, if we remember, I'm going to put a number 2 here so you know this is the work for problem number 2. Power is equal to our work over some time. Okay, and if we look up top here, we know that our work is equal to some force times some distance, and so our power is that work over time. And so again, we have our 200 newtons times our 4 meters. Maybe I should put units on here, hold up. 200 newtons times 4 meters divided by 4 seconds. And clearly, as you guys can see here, hold up, just change. Orange probably isn't the best color. There we go. As you can see here, 4's cancel out, so we should just be left with 200. But not our meters and seconds don't cancel out, so we still have a newton per meter per second, which we also should know as a watt. Okay, and you should know that just looking at this, we're looking for power. Okay, and power is measured in watts. Hopefully that one made sense. Moving on to number 3. So far, fairly easy, hopefully. Fairly straightforward at least. Okay. Number 3 here. Well, let's put the work, my written work, not the work, mechanical work. Little joke, I guess. Probably not. So number 3, work. Okay. Power is work over time. My work here, you can see that the engine does 60,000 joules of work. So we have 60,000 over our time, which is 10 seconds. So we have our joules per second, which is also watts. Okay, we can just do quick, we don't need to bust out our calculator. Take away a 0 there, take away a 0 there, and we're left with 6,000 watts, also known as 6 kilowatts. Right, 6 kilo means 1,000, so 6,000 watts. Okay, moving on to number 4. The big one. If you were in class, hopefully you paid attention while we were going over this. This is one of our inclined plane problems, which requires us to do trigonometry, which some of you might not be too excited about. So, to start with, sorry, I'm trying to slide this up. That didn't work. Oh well. Okay. We're given the block of ice weighs 500 newtons. Okay, it's important to know the distinction of units. When it says 500 newtons, that means the force of weight, okay, not the mass. If this were to say an ice block weighs 500 grams or kilograms, then we'd be talking about mass. But because it says newtons, we know this is force. Okay? So, our force weight always acts from the center of our object straight down. In this case, we know it's 500 newtons. If we are on a flat plane, if this ice block were on a flat surface or in free fall, our force normal would typically be in the opposite direction, and it would be equal and opposite, so it would also be a 500 newtons. But because we're on this inclined plane moving up this ramp, we know our force normal translates and remains perpendicular to the surface. So the surface that we're talking about is the ramp here. I'm doing some dotted lines so I don't confuse people with a ton of random lines everywhere. So if I draw a line perpendicular to that line, it should look something like that. Whoops, like that. Okay, and we call this our force normal perpendicular. But are we looking for, in question A, are we looking for our force normal perpendicular? No, we're looking for the force parallel. Okay, parallel means running in the same direction. They're never going to cross the path. So if we look at this line that's running up the ramp, we know that our force parallel needs to be parallel to that. Okay, and the way that I'm getting these lines, I'm not just drawing them randomly in this triangle. Okay, we know that this force normal, that's the 500 newtons here, can be broken up into its vector components, right? If my coordinate system runs like this, and this is my y line, and this is my x coordinate, then we know this 500 newtons vector runs somewhere in between the y and the x, which means it's a component of y and x. In this case, though, we're not calling these lines y and x, we're calling them perpendicular and parallel. Force normal parallel. Okay? Stick with me while I erase everything that I just did so I don't confuse everybody. Okay, and I'll rewrite force normal parallel. So we're looking for a force normal parallel. So we're trying to solve this, but we only have one side of this triangle. We can't solve the other sides without at least two sides, or one side and some angle theta. That's not a very good theta. Let me change the thickness of this pen. Go theta. Whatever. And so going back to all the way to geometry, and you probably heard me say this in class, but we know based off our geometric theorems that based on alternate interior angles and having symmetric triangles, that this angle should also be equal to theta. So that inside angle of the bottom ramp and the inside angle of this top triangle are the exact same angle. And we calculate this by using our trig functions. Our SOHCAHTOA. So if I look at this bottom ramp, I have my horizontal here, which is touching my angle. Okay, but it's not the longest side of the triangle. The longest side of the triangle is at 6 meters. And we know that the longest side of our triangle always is the hypotenuse, which means that this bottom line has to be our adjacent. Also, we know that the one side of the triangle that isn't in contact with the angle, we call that the opposite side of the triangle. So by default, this becomes our opposite side. In this triangle, we know 3 meters and we know 6 meters. So we basically know our opposite side and our hypotenuse side. So we need to go back to our SOHCAHTOA and look at which one of those trig functions include opposite and hypotenuse. Well, it's sine, opposite, hypotenuse. So that means we need to use sine. The way we set this up is sine of my angle, which in this case is unknown, so we just leave it as the variable theta, is equal to my opposite side, which is 3 meters, divided by my hypotenuse side, which is 6 meters. Okay. In this form, we can't yet solve for theta because we don't have it isolated. We need to isolate variables in order to solve for them. So what we do is we have theta, and then we end up taking the sine inverse, okay, of 3 over 6. And I'm just leaving those meters off because meters divided by meters cancels out. So we're left with sine -1 of 3 over 6, or 1/2. And if you plug this into your calculators, hopefully you know how to do this. If not, make sure you come and ask me in class how to get this sine inverse. If we plug this into our calculators, we should get theta equals 30 degrees. 30 degrees. So this equals 30 degrees, and this equals 30 degrees. So now we have one side of our triangle and we have an angle. So now we can finally solve for this force normal parallel. And I'll slide over. So now I'm solving this triangle. And again, we're dealing with angles, which is trig. So we're going to need our trig functions again. And if we look at this triangle, the longest side of this upper triangle is the 500 newtons, which makes it my hypotenuse. The side that we're interested in, the force normal parallel, is not touching my angle. So that makes it my opposite side. So again, we're dealing with hypotenuse and opposite, which if we look back over here is sine. So we're going to use the sine function again. So I have sine of my angle, which I now know to be 30 degrees, is equal to my opposite side, which is unknown, and we can either write force normal parallel or x. It just needs to be represented as some variable that we're going to solve for, over my hypotenuse side, which is 500 newtons. And the way we solve this equation is by multiplying both sides by 500. On this side it cancels out, and I'm left with x on that side. And now I have 500 times sine of 30. So x, or x equals force normal parallel, which equals sine of 30 degrees times 500. And when you do that in your calculator, 500 times sine of 30, the parallel force, right? This parallel force is equal to 250 newtons. Okay. So now problem B. Okay. I'm just gonna erase some of this stuff that might be covering up some other things. Problem B. Okay, how much work is required to push it up the incline? So to push it up the incline, that means we're dealing, oh shoot, I have it on erase still. That means we're dealing with a force going up the incline like that. And we just calculated that force. That force is that 250 newtons. So we remember work is the force times the distance. In this case, it's my 250 newtons, and my distance is my 6 meters. When we do that, 6 times 250 gets us 1,500 units of work, joules. Okay? Problem C. What is the potential energy of the block relative to the ground? So now we're saying if at the very top, if we push the block all the way to the very top, how much potential energy does it have? Potential energy equals the mass of the object times gravity times the height. Okay. Well, do we know the mass? No. We know the force weight, so we can solve for the mass. But we also know that the force weight is equal to mass times gravity. Well, do we have mass times gravity in our potential energy equation? Yeah, we do. Mass times gravity is our force normal, which is our 500 newtons. So all I need to do is take my 500 newtons times the height. Now it's not this length of the ramp anymore, it's now the height. And it's how high it is from the ground, or the 0 point. In this case it's 3. So hopefully you guys, I'm just going to kind of do this in my head because I'm running out of space. 3 times 500 should again get us 1,500 joules. So we're already kind of seeing some of these answers are coming out the same. So let's kind of start thinking about why that might be. And then problem D. What would the potential energy of the block? What would be the potential energy if the block were simply lifted vertically 3 meters? So I'm going to change the wording of this problem, and I'm going to cross out potential energy, and I'm going to say what would be the work if the block were lifted. Because when something's lifted, it implies that it's moving, which means that it's not really potential energy if it's moving. So we call it work. And our work equation is the force times the distance. And in this case, if we lift it straight up, that means that we're lifting all of the weight. Nothing's helping us, right? So we have to lift all 500 newtons of that weight up the total amount of distance, which in this case is the vertically 3 meters. So again, we have a force of 500 newtons times a distance of 3 meters, again equals 1,500 joules. So the takeaway from this is that no matter which way, whether you're pushing it up a ramp, this block of ice, whether you're pushing it up the ramp, or if you're just lifting it straight up, you're going to spend the same amount of energy. So the energy equals the same. So you might be thinking, well, what the heck? If I have to spend the same amount of energy, why would I do either? Maybe, I don't know, if I can lift this, it's just easier to lift it instead of building a ramp and sliding it up. The thing is, though, that ramps are what we call simple machines. And simple machines allow us to have mechanical advantage. And why we like mechanical advantage is because it literally plays to our advantage of when we can no longer, lift something or move something that is beyond our capability to move. Or we just want to make it easier for ourselves to move. So the key comes in the force, right? Down here for problem D, my force was I have to lift the entire box. I had to lift all 500 newtons of it. But in problem A, I only had to slide it up the block with a force of 200 newtons or 250 newtons. So by using the ramp and therefore using mechanical advantage, I was able to move this block the same amount with half the energy, or with half the force. With half the force, but I get the same amount of energy out of it, or I spend the same amount of energy. So that's essentially what mechanical advantage is. Problem 5. Okay? All the ramps below are 5 meters high. We know that the kinetic energy of the block at the bottom of each ramp will be equal to the loss of potential energy. This is known as conservation of energy. Okay? We want to find the speed of the block at the ground level in each case. We recall from earlier chapters how much time it takes something to fall a vertical distance of 5 meters from a position at rest, assuming that gravity is, they're rounding up. We usually say 9.8 meters per second squared. They're just rounding up to 10 to make easy math calculations. And how much speed a falling object requires in this time. This gives you the answer to case 1. Okay? Discuss with your classmates how energy conservation provides the answers to case 2 and 3. So, we can solve this using our conservation of energy equation. Basically, what our conservation says is that we know that all the kinetic energy of the block at the bottom should be equal to all the potential energy. So our potential energy equals our kinetic energy. And if we look at our equation formula, potential energy equation is mass times gravity times height. And our kinetic equation is 1/2 mv squared. Where you're looking at this and you're saying, okay, gravity we know 9.8, height we know 5 meters, velocity we're looking for mass. Okay, and nowhere in here does it say mass. Well, the trick is that we don't really need mass, because if you notice your equation, you got mass showing up on both sides of the equation. And when mass shows up, or when any variable shows up on both sides of the equation, that means it can just simply divide out, right? If I divide mass from this side, I have to divide mass from this side, and therefore they cancel out on both. Okay. So basically there we're left with now that our potential energy is gravity times height is equal to 1/2 v squared. So now we know gravity, we know height, and now we can solve for the velocity. So gravity is 9.8, or we can round up to 10 for simple calculations. Our height we know is 5 meters. And then we have 1/2 v squared. So to solve this, I just divide both sides by 1/2. And let me see if I can write this over here. So I have 10 times 5 divided by 1/2 equals v squared. This 10 times 5 is 50 divided by 1/2 is 100. Whoa, turn my O into a hexagon. Equals v squared. Then to solve this, I just take the square root of both sides. Square root of 100 is 10. So I get 10 meters per second. Now the cool thing with energy, potential energy, and conservation of energy, okay, is that it basically just deals with how high something is off the ground. So because these are all at the same height, we could say that they have all of the same potential energy. Whether it starts here and falls to the bottom, or it starts here and rolls down this ramp, or it starts here and rolls down this ramp. Right? It doesn't matter. They all have the same potential energy. And if they all have the same potential energy, that means they all have the same kinetic energy. So at the bottom, all their kinetic energies are the same. Or at any point. Say that the ice block was at this point, and at this point, and at this point. If they're all at the same height, then all their kinetic energy is the same. And if their kinetic energy is the same, then, and we haven't changed the mass, right? Our kinetic energy equation, 1/2 mv squared. If we haven't changed the mass of that block, then we know their velocities have to be the same if they're at the same height off the ground. So because these are all on the ground level, that means their speeds are all 10. And I know what you're probably thinking. Well, they're on the ground, so isn't their speed technically 0? Well, in physics, when we always talk about how fast something's going, like right before it hits, because we know, like, obviously when it hits the ground, it's gonna stop. It's gonna be 0 velocity. So we want to calculate how fast it was going right before it stopped. So right before this block stopped, it was traveling at 10 meters per second. Hopefully that made some sense. Moving on. Okay. So which block reaches the bottom of the incline first? Assume no friction. Be careful. Explain your answer. I don't really like this be careful. That kind of implies that it's not what you think, which is completely wrong in this problem. It's exactly what you think. Okay? But we're just going to explain it using our energy. So again, the blocks are relatively at the same height. Okay, that corner of A is the same height as that corner of B. So we can say that they have the same amount of potential energy, which means when they go to the bottom, they're going to have the same amount of kinetic energy, which means that they're going the same speed. So if this asked which one was going to have the biggest speed, then you'd have to be careful because they'd actually have the same speed at the bottom. But if you look, ramp A only has to go that far. Ramp B has to go that far, which is a longer distance. So even if they're traveling at the same speed, it's going to take an object longer if it has to go a farther distance. Therefore, as you probably guessed, block A will reach the bottom of the incline first because it has a shorter distance to go. Hopefully you can read this chicken scratch style pen writing. Hopefully me talking through it makes it maybe a little more clear. Problem 7. Okay. Both the kinetic and potential energy of a block freely sliding down a ramp are shown below only at the bottom position in the sketch. Fill in the missing values for the other positions. So we know, due to conservation of energy, that whatever we have in a total of kinetic energy and potential energy is what we have throughout, right? So if we add these up, the total amount of energy we have is 75. So that means up here at the top, we cannot have any more than 75. So if my kinetic energy is 0, then that means everything has to be potential at that point, which means at that point we have all 75 joules. At this next point, we'll call that position 2. Again, we cannot create or destroy energy. If we start with 75 joules, at every point on this block, we need to have 75 joules. So if we have 50 joules of potential energy, that must mean we have 25 joules of kinetic energy. And then at position 3, if we have 50 joules of kinetic energy, that must mean we have 25 joules of potential energy. Pretty straightforward. Problem A. A big metal bead slides due to gravity along an upright friction-free wire. It starts from rest at the top of the wire as shown in the sketch. How fast is it traveling as it passes point B, point D, and point E? Okay, so again, we're going to have to use our law of conservation of energy, which is our potential energy is equal to our kinetic energy, which means that our mass times our gravity times our height is equal to 1/2 times our mass times how fast we're going, or our velocity squared. So at point A is where we start. It's at rest, right? It starts from rest, which means if it's at rest, it's not moving, which means we have no velocity. So our kinetic energy is 0 at that point. Okay? our potential. We have lots of potential energy though. We have whatever the mass of this bead is times gravity times height. But if we just set it up that way, mass times gravity times height, we wouldn't be able to solve it because we don't know what the potential energy is yet. So we have to set it equal to whatever the speed is going to be at position B. And in this case, when we set it up this way, we have mass on both sides of the equation, which means they basically just cancel out. And we're left with gravity times height equals 1/2 v squared. So again, I know gravity is 9.8, or I can round that up to 10, so I can do the math in my head. Times the height is 5 meters. I shouldn't leave off units, but I'm going to just because I'm running out of space. 5 meters. As I say that, I write the units. I don't even know what I'm doing anymore. I don't know what's happening. Oh, just stall that. So 10 times 5 meters is the height equals 1/2 v squared. Again, I divide both sides by 1/2. I'll just say 0.5. And then 10 times 5 is 50 divided by 1/2 again is 100. So then I have 100 equals v squared. Take the square root of both sides. And again, I get 10. So at point B, at this difference of 5 meters, right, that's what we used for our height, point B is going to travel at 10 meters per second. Now, the cool thing about energy, again, is that it deals with the height. So all the potential energy that was up here at A is transferred to kinetic energy throughout this entire thing. At each of these points, it's transferred to some kinetic energy. But in this case, we're concerned with this dotted line because that's where our point B and our point D and our point E lie. So because point B and point D and point E are all on this same dotted line, which means they're all 5 meters away from where our potential energy started, that means that all of their kinetic energy is the same as well. And again, we remember if all our kinetic energy is the same and we haven't changed the mass of the bead, then that means that our velocities must be the same. So at point B, and point D, and point E, all our velocities should be the same. Now, it says maximum speed occurs at which point? So we know that if they're all at the same point, they're all going to be traveling at the same speed. So in order to get a speed faster than that, well, it needs to drop some distance more or some more height. So we could say this is 1 extra meter. So in this case, the potential energy then would be 10 times 6 meters divided by 1/2, which is then 120, and the square root of that is, I'm not sure, it's obviously bigger than 10, right? So that means that our maximum speed occurs at point C. Okay. Rows of wind power generators are used in various windy locations to generate electric power. Does the power generated affect the speed of the wind? Would locations behind the windmills be windier if they weren't there? Discuss this in terms of energy and conservation with your classmates. Okay, so the key here is that we want to talk about this in terms of energy. And when we think about this, the whole point of having wind turbines is that it generates energy. And again, we can't just create energy. So even though that wind turbine is turning and powering or creating energy, sorry, I shouldn't say creating, is producing energy, it had to come from somewhere. And it came from the wind. So in order for this to make sense, for the wind turbine to operate, it needs to take some of its energy from the wind. So all the wind in front of the turbine is then translated into all the wind energy in front of the turbine is converted into electrical energy by the turbine. So due to our conservation of energy, if I'm taking out some of the energy of the wind and turning it into electrical energy, then that means that wind energy after the turbine has to be less, right? So would the locations behind the windmills be windier if the windmills weren't there? Yes, it would be. Okay, and we can say yes because energy, or let's say this keeps taking a second to, because electric energy, and I just NRG, energy, whatever, because electrical energy in turbine or windmill comes from wind energy. Therefore, there is less wind energy after windmills turn. I don't know. This kind of got contrived very fast, but hopefully it made sense. I mean, I got turbines and windmills and wind energy, and yeah, hopefully that made sense. If it didn't, I have a little picture here to show you. Maybe this will hopefully illustrate it more. This is a picture of wind turbines off coast. I'm not sure where exactly, but it's obviously in a morning where they had some heavy fog roll in, and you can see the turbulence of the wind after it goes through the wind turbine and produces energy, right? So we can see over here we don't really see any wind, right? Because it's flowing naturally, and then as it goes through this turbine, it becomes what we call as turbulent. Okay, and which means that it's moving really sporadic and really kind of out of control. And it's doing that because all this nice flowing laminar, which you guys don't really know what this is, but laminar means like a nice smooth flow. All this nice smooth flowing wind on this side is then translated into electrical energy by the turbine, and whatever's left kind of just moves around in this weird chaos. So when we have this nice energy and we put a wind turbine there, then we get less wind behind it. And this comes into play when we talk about we won't talk about it, but in industry, when they look at where would wind turbines be the most effective, this is something important that they have to look at. Because if you see that they have this wind turbine in front of this turbine in front of this, you can see that this next turbine is getting all this kind of crappy turbulent wind, and so on and so forth, and it keeps getting worse and worse and worse, which means that this turbine is going to be less efficient than this one, and this one's going to be less efficient, and this one's going to be less efficient. So really, you got to pay attention to stuff when you're producing this wind farms. And you can't just put stuff wherever. You have to really pay attention, and you have to know your laws of conservation of energy. So whoever designed this might not have known their laws of conservation of energy very well. Maybe it's just a picture, who knows. But hopefully this all made sense, and hopefully you guys learned something. If not, hopefully you guys can come to class with some questions, and we can answer them in person. But if you've made it this far, then thanks for watching, and I'll see you guys at another time.